Honorable Director, Professor Dr. Ajit More, Assistant Director, Dr. Nilesh Mate, Resource Person for today's guest session, Dr. Jyoti Yadav, respected faculty members, coordinators from various centers across India, our technical, administrative, and support staff, and dear students. A very good morning to one and all present here. On behalf of Bharati Vidyapeeth deemed to be university and Center for Distance and Online Education, I, Dr. Seema Tarnekar, Program Coordinator MCA, extend you a very warm welcome to this guest session on blockchain technology, organized for MCA and BCA students. Bharati Vidyapeeth, established in 1964, has been a pioneer organization in the field of education and has created landmarks in its journey. Bharati Vidyapeeth, deemed to be university, has been re-accredited by NAC, National Assessment and Accreditation Council, with A+ grade in 2017. It is also been awarded Category 1 university status by UGC. The university has been continuously ranked among top 100 universities in India by NIRF, National Institutional Ranking Framework, Ministry of Education, Government of India. Now, I would like to request Professor Dr. Ajit More, Director, Center for Distance and Online Education, to address the audience. Over to you, sir.
Am I audible, ma'am?
Yes, sir.
Very good morning, all the participants for today's guest lecture on blockchain technologies. And the expert, Yadav ma'am, she will be delivering the talk on blockchain technologies. Friends, the distance and online education of Bharati Vidyapeeth always try to arrange the lectures and the series of talks by the experts in various fields, which will be helpful to you in your academics. And looking into this particular point, we have organized today's lecture. Blockchain technology, as you all may be aware, that this is one of the technology which is trending like other trends like artificial intelligence, machine learning. So all these new concepts which are coming and which
सर
are
स्क्रीन नहीं दिख रहा है
which are I'm not sharing any screen.
Screen is visible, sir.
Yeah. So this particular lecture is basically to acquaint our student with the concepts of blockchain and its application in real world. I'm sure that after attending today's lecture, all student friends will be comfortable and will be acquainted with the concept of blockchain, and they will be in position to use this concept in their projects or the assignments which are given to them, or if they once they join the organization, then will be equipped with the latest concepts which are trending in IT. So I request all the students and the faculty members, whenever we organize such session, please attend those sessions, ask the question to the experts, because it is very rare that experts are coming to you, and this is an opportunity for all of us to ask the questions, clear your doubts, so that you will be well equipped with these new academic concepts. So thank you once again, and I welcome you all for this particular guest session. And over to you, Tarnekar ma'am. Thank you.
Thank you, sir. Now, I would like to request, hello.
Yes, ma'am. You're audible.
Okay. Thank you, Dr. Ajit More, sir. Now I will take this opportunity to introduce our today's resource person, Dr. Jyoti Yadav. Dr. Jyoti Yadav is currently working as faculty member in the Department of Computer Science, Savitribai Phule, Pune University. She has 26 years of teaching experience. After completing post-graduation in computer science from Nauroji Wadia College, she qualified the UGC NET examination in computer science. She has received the first rank during the MPhil Computer Science degree in the year 2009 and received PhD degree in Computer Science in the year 2015. She has 20 papers published in peer-reviewed international journals of high repute. She has 9 chapters published in different books with IEEE Explore, Wiley, ITI, and Springer publications. She has presented many research papers in international and national conferences. To her credit, she has worked on minor and major research projects in Pune University. She has been an invited speaker at various international, national, state, and university level conferences, workshops, webinars, etc. She is recognized guide in Pune University in the subject computer science and is guiding 5 PhD students. 2 students have been awarded PhD under her guideship. She has published 3 patents also. She is a member of Board of Studies in Computer Science at
भरतला बोलवा
SP College,
आणि
Garware College,
भरतला
Nauroji
तर
Wadia College, Modern College, St. Miraj College,
आणि तो काय
etc.
नाव सौरभ
Her research areas include soft computing, artificial intelligence, machine learning, cloud computing, software defined networks, deep learning, and blockchain. Dr. Jyoti Yadav, madam, I welcome you and request you to take over the session.
Thank you so much, ma'am, for the introduction. Am I audible?
Yes, madam.
Okay, I'll just share my screen. You just let me know whether it is visible.
Okay, okay.
Is the screen visible?
Yes, madam.
Okay.
Yes.
Yeah, so let's begin with this, a buzzword called as blockchain. So delving into blockchain, and most probably in these 2 hours of session, I'll be able to give you just a comprehensive overview of what blockchain actually is. Okay, now this word blockchain actually came into being when, when Modi government's demonetization drive had started. And that gave initiative to this digital transactions. And there was a lot of debate on blockchain. But why blockchain came into existence, or why importance was given to blockchain, was because of their security features and the easiness in transactions that were initiated online. And even the tax authorities, they were also happy, since digital transactions could be tracked very easily as compared to the manual transactions, or you can call them as paper counterpart. So this was the reason why blockchain was important to us, and they started studying about blockchain. So in this lecture, the plan of attack would be, I'll talk about the history of blockchain, the applications of blockchain, what is blockchain, understanding the SHA-256 hash algorithm, because this is the main algorithm, which is the you can say the heart of blockchain. Then we'll talk about some concepts related to blockchain called as immutable ledgers, distributed P2P network, how mining works. In mining, we need to know the terms called as nonce and cryptographic puzzle, because this is the whole concept of blockchain here. And then the last point we shall talk about is the Byzantine fault tolerance. So talking about, and the consensus protocol. So talking about the history of blockchain. So blockchain actually has the potential to grow to a bedrock of the worldwide record keeping systems. So basically it was evolved because we want to keep records which are historical. So they were just launched, 10 years back, and it was created by some unknown persons behind the online cash currency called as Bitcoin. So you must have heard about this term called as Bitcoin. Bitcoin is nothing but it's a cryptocurrency, and this was initiated by under the leadership of a scientist called as Satoshi Nakamoto. So typically blockchain as a concept was there in various forms earlier as well. So in the diagram of blockchain, the evolution is basically divided into three parts: the origin of the blockchain, contracts, and the third part is the apps. So in 1979, the first year when blockchain actually started developing, we talked about the Merkle trees. So there was a concept which was called as a Merkle tree, which was proposed by Ralph Merkle in 1979. Okay, so this was just a way to initiate blockchain. And then in 1991, a cryptographically secured chain of blocks was described for the first time by Stuart Haber. So this person, Stuart Haber and Scott Stornetta, these two people actually came up with a cryptographically secured chain of blocks with this concept. And then they thought that if we timestamp the digital documents, then these timestamping of the digital documents, like how to go about timestamping and how to save this digital documents. So this idea was basically initiated by Stuart Haber and Stornetta. So securing, like you need to secure the timestamps of the documents, like when they were created, when they were updated. So whenever any digital document was created, we need to timestamp that, like what time, what date the document was created, or what time or what date it was updated, and so on. So all this timestamping of digital document was very important. So they thought like we'll use this concept in blockchain and try to evolve them. So, and of course, when we are talking about digital documents, when we are talking about security of digital documents, then we need to see that these documents are going to be tamper proof. So we should not be able to, we should, in the sense, nobody should be able to tamper with the digital documents. Then in 1998, there was a computer scientist called as Nick Sabzo. He worked on bit gold. Just similar to Bitcoin, we had a concept of bit gold, which was a decentralized digital currency. And he thought of applying the concept to this particular currency. In 2000, there was a scientist called as Stephen who published his theory of cryptographic secured chains. And he implemented the concept of cryptography there. And in 2008, Satoshi Nakamoto, he was the first person who came up with the concept of blockchain technology. And he released his first research paper, which established the model of blockchain. So this is where he starts talking about, he created Bitcoin, he introduced the concept of blockchain to abstract distributed ledger, which was maintained by anonymous consensus. And then in 2014, blockchain technology basically started evolving, and it was captured by the financial markets. And these financial markets like JP Morgan and all these financial giants, they started using the blockchain technology, and some apps were also evolved. So this is the generation where in 2013 and 14, it started taking a proper shape. And then we talk about the last generation where we have these permissioned blockchain networks. So here, like I told you that initially we had the concept of blockchain, and then this is the origin of blockchain in the first part. The second part, we are talking about contracts. Like here, the smart contracts was developed. And then finally, we have these apps here in after 2016. So this is the origin, and then the contracts, and then the apps. So this is how blockchain has been evolved, and usually we call this as a second generation. Like other blockchains, which include you can run different types of cryptocurrency coins. So basically, the first blockchain was developed for Bitcoin. And then we'll see there are there are different cryptocurrencies like Ethereum, there is Ripple, okay, Zcoin, and so on. So there are various cryptocurrencies, but Bitcoin was the first one which actually used the concept of blockchain. So there are 9 verticals of blockchain transformations, like which are the areas in which we can actually apply blockchain or implement these applications using blockchain technology. So the first is technology. Technology with respect to, like we hear about artificial intelligence, we hear about cloud computing, cybersecurity, Internet of Things. So all these are technologies where we can, integrate blockchain technology with it. So these are the various fields where technology is also important. Then we have entertainment like the music industry or the entertainment industry, where we really talk about the ownership rights or the copyrights, or we have, like if we have the music related to music industry, we can say that we cannot have any illegal downloads. Okay, because nowadays you see that there are so many groups in even in Telegram where even a new movie can be downloaded, but it's illegal. So you need some copyright for these downloads to be done. So can we use blockchain for the music industry or for the entertainment industry where all these things could be taken care of? Then we have the advertisement sector, that is the media, where we talk about low cost advertising and marketing, or we want to do the advertisement but we do not want to involve any intermediaries. So how do you handle this? So this is one of the areas where blockchain can be used. Law and crime, where we are talking about this police law, okay, or probably the gun safety law. So where we with respect to law, when we are talking about preserving the evidence or no falsification of data or timestamps, or how the chain of facts can be collected, or how to track the criminal IDs, and like to preserve the ownership of gun possession and so on. So in this area too, blockchain can be applied. Then we have transportation. In transportation, we talk about the public transportation or the business transportation. Public
Excuse me,
transportation
ma'am.
for, yes.
Ma'am, this is Niket this side. You're still showing the first slide. It's not moving. Are you on first slide or
Yeah, I've
not?
moved to the second, third, fourth slide.
Oh, no,
Okay, let
still
me
it is
share it
on.
again.
Again, yes, yes.
Now, is it visible? I'll just
Yes,
shift
ma'am.
the screens.
Yes, yes, yes. Now it is perfect.
Just tell me whether it's moving to the next screen.
Yes, ma'am. Yes, it is moving.
Yes? Okay.
Okay.
So in the 9 verticals, I was talking about technology, entertainment, media, law and crime, transportation, and now the government sector. Like in transportation, we talk about the business transportation, where we talk about how to access the trip data or how to track the path of the vehicle. Or in public transportation, we talk about how the payments can be made accurate, or how the ride sharing can be done, and so on. And in the government sector, we talk about the transparent voting system, so that we minimize the fraud, and we talk about the citizens' right. And maybe in the government sector, or in the transport, or in the travel sector, where we talk about the travel information, the boarding pass, passport boarding information, or passenger identification, or for that matter, healthcare services. Can we have a entire patient database management system, or drug supply chain management? All these things, or these are applications where blockchain can be used. And then we have contracts. In contracts, we talk about inheritance, or property, like land property, for example. So if for land property, how the property information can be stored, uh, should, like, because we need transparency in the payments, we should know, and even in the ownership charges, like who is the owner of the property, all this has to be transparent. So we can use blockchain in this case. Finally, we have this finance sector. In finance sector, obviously we are talking about the financial protection or the banking interface. So financial protection with respect to insurance, maybe agreement preservation, validation, or you validate the agreement or the entire transaction process. With respect to banking interface, it's very necessary that you have a very secure transaction. So, and we assume that blockchain is secure. So as of now, since we are not aware of what blockchain is, so maybe by the end of the lecture, we can say that yes, blockchain is very secure and we can use it for all these applications. And finally is the human rights and contributions. Contributions in terms of maintaining the donation integrity, or you want to ensure safe fundraising channels, or there are some voluntary organizations where, you know, tracking all donations and ensuring the security, or you you need to ensure the integrity of the donator, and you reduce the overall complexity of the process. So this is the entire 9 verticals of blockchain transformation, and it's a open field and it's just evolving. So there are many things that you can do in this particular field. Next, let's talk about the foundational concepts of blockchain. Now, this statement is very important. Like it says that the blockchain will do to the financial system what the internet did to the media. And this is a statement which was published in Harvard Business Review. Now, the technology most likely to change the next decade of business is not only the social web or the big data or cloud or robotics or even for that matter artificial intelligence. It's the blockchain, the technology behind digital currencies like Bitcoin. Now, now it's very complex. Like blockchain technology is very complex, but the idea is very simple. So at least let's talk about the idea. So at its most basic, blockchain is, we can call blockchain as a global distributed ledger or a global distributed database, which is running on millions of devices. Because I'm talking across the globe. So just imagine how many devices can be connected to this blockchain. And it's open to anyone. When we're talking about a public blockchain means it's open to anyone, where not just information, but anything of value can be stored. Now make a note of this particular statement. Like, we are not just storing information here. We are storing something that is of value. For example, it could be money, that is financial transactions. It could be titles in the sense property titles, or it could be deeds or some agreements. It could be some agreements related to music, copyright issues, or some scientific discoveries. Scientific discoveries, property, not only I'm not talking only about physical property, but it could be intellectual properties as well. I can also use to store, I can develop an entire e-voting system using blockchain, where we are trying to minimize the fraud. So there's no tampering with the votes will happen. So this could be a technology which can, you know, take over the current voting system, and it can replace that. So blockchain basically, it ensures integrity and trust between strangers. Now, why strangers? Because if I am one person sitting at one corner of the world, I can be connected to some other person sitting at the other corner of the world, and we are unknown to each other. So we are strangers. But still, blockchain will ensure this integrity. Huh? And this will make blockchain, like nobody can cheat. On the blockchain, nobody can cheat. So in other words, we can say that it is the first native digital medium for value, just as the internet was. Like the first native digital medium was internet for information. So whatever information we wanted, we used to search the internet. So these, and of course, like whatever information we are going to search, or for whatever purpose that we are going to search, it has big implications on our businesses and other administrative sectors. So much of the hype around blockchains, it has the focus on their potential to fundamentally change the financial services. So basically, it was started for the financial area. And maybe in the next coming generations of the internet, we'll focus on value as well as information. Because till now, the first generation was focusing only on information, but now we need to talk about value as well. So blockchains may radically drop many transactions cost. And we'll see that how. I'll give you some examples like related to banking sector and how we pay some extra amount. And if we use blockchain, what will be the advantages? So first we need to understand the concept of what is centralized versus decentralized versus distributed network. So in centralized system, as you can see the picture here, all the nodes are connected under a single authority. So all users are connected to a single network owner, or we'll call it as a server, and the central owner stores the data which other users can access. Okay, so data, it could be data or information, anything. So this user information it could include user profiles or some user generated content or anything. A centralized system is basically, it's very easy to set up and it can be developed very easily because you just need one server, and to that server you're connecting all the clients. But this system has an important limitation. If the server crashes, then the system is no longer going to work properly and the users cannot have access to the data because there's only one server. And it could happen that if the server fails, then all the clients will have some problem in accessing the data, because a centralized system needs a central owner, and this central owner is going to be connected to all the users and the devices, and the network will be available only if the centralized server is working fine. So everything depends on the owner, and owner is the central server. So, and if you look at the security concerns, when one owner stores user data, and it's very easy to understand why centralized systems are nowadays not a first choice. They are not the first choice for many organizations because of the security concerns. Then we move on to decentralized network. In decentralized systems, no single authority server controls the nodes, and they all have their individual entity. Now, this single server in the centralized network has been replaced by, you have some 6 servers here. So it is decentralized. So if if this server was performing some end task, now it is being distributed among 6 servers. So as its name implies, decentralized systems don't have a central owner. They have multiple central owners, each of which usually stores a copy of the resources users can access. So each server here will have some copy of resources. Resources, it could be in terms of data, it could be in terms of information, it could be in terms of devices, or maybe one server, like the clients may require some resources with respect to IO devices, anything. So every server is storing some copy of resources. So a decentralized system can also suffer from crashes, just as the centralized one. But it is by design, it is more fault tolerant, because even if one server in this distributed or in this decentralized network goes down, other servers can take. Okay, the system is not going to fail. The server can fail, but the system will still continue to operate. So we, in this sense, we can say that decentralized networks or decentralized systems are more fault tolerant than the centralized networks. Okay, so even if there are crashes, the system won't crash. And finally, we talk about the distributed system. So you can see that in this distributed system, if you compare it with the decentralized system, so here also we had some multiple servers. So here also we have multiple servers, but these clients are not dependent only on one server. They are all connected to each other. You can see even the clients are connected to each other. So this makes a distributed system. It is very similar to decentralized one, in that it does not have a single central owner, but going step further, it eliminates centralization. So basically in a distributed system, users have equal access to data through user privileges. Like we can give privileges. Privileges can be enabled to the users. And the best example of this vast distributed system is the internet itself. So internet is an example of distributed system. Now, this distributed system will allow the users to share ownership of data as well as resources. So we have some hardware and software resources that are allocated between users, and maybe in some cases it is allocated in such a way that it improves the performance of the system. And a distributed system is safe from independent failure. Just as like if we compare it with the centralized network, in centralized network there was a server which fails, a single server. So this disadvantage of the centralized system is overcome in the distributed network. So it is safe as compared to centralized network or as compared to decentralized network. So the major advantage, basically, to just to sum up this slide, is that of distributed system over single computers is we can get high computing power, a lot of cost is reduced, high reliability, and ability to grow naturally. Because there are, if you look at this network, like tomorrow I get my new laptop, I can connect it to the network. So there are so many n number of nodes getting connected to the distributed network. So it has an ability to grow naturally. It does not have any it does not suffer from any scalability issues, right? So this is the beauty of distributed networks. Then, since I also mentioned that blockchain is a database, or you call it as a blockchain database, so we need to compare blockchain databases with centralized databases. So how it is different? So we will call this as a traditional databases. So this traditional databases usually are centralized, but blockchain functions in a totally different way. A blockchain stores information in blocks, and these blocks are of uniform size. Like if I call this as the entire block, this is a block, this is a block. Each block is going to be of uniform size. Each block contains some hashed information, or we, as of now, we'll just call it as coded information. Okay. And the coded information is stored in such a way that each block has a hash key, and this key is helping us to connect all the blocks in such a way that the hash key of the second block acts as a previous key of the first block, and so on. So this pattern is followed, and that gives us the chaining effect. So in the forthcoming slides, I'll explain this in detail. So unlike databases, this becomes an added security feature with blockchains, and databases do not have this cryptographic security. And obviously, blockchain uses the hashing algorithm called as SHA-256, which is a very wonderful hashing algorithm, and it is made so secure that nobody can tamper with that algorithm. So this is how blockchain differs from centralized or traditional databases. Inventors of blockchain. Now the 21st century is all about technology. We are talking about technology. So many new technologies are coming. And with this increasing need for modernization in our day-to-day lives, people are open to accepting new technologies. Like even in the pandemic years, for the last 2 years, we adopted, like people learned so many different technologies. So we as humans are ready to accept the technologies. So from using a remote for controlling the devices to using voice, like you have those voice assistants for giving commands like Alexa, Siri, or you have this Cortana for Windows and so on. So these are all voice assistant, and that is making our life very easy. So technologies like IoT or augmented reality, for that matter, if you have heard about it, it has gained a lot of pace in the last decade. And now there's a new addition to this, that is blockchain. So blockchain, we'll call this as a revolutionary technology, which is impacting different industries. And it was introduced in the markets with its first modern application as Bitcoin. So Bitcoin is nothing but a form of digital currency, or you call it as a cryptocurrency. Bitcoin is not blockchain. Remember this. If you say that what is blockchain, blockchain is Bitcoin. So this answer is totally wrong. We can say that Bitcoin is a digital currency, and it is the first application of blockchain, right? The underlying technology behind the success of cryptocurrency Bitcoin is blockchain. So that is the technology. And there's a common misconception among people that Bitcoin and blockchain are one and the same. So that is not the case. So creating cryptocurrencies is one of the applications of blockchain technology. And other than Bitcoin, there are numerous applications that are being developed on the basis of blockchain technology. Okay. So what exactly are bitcoins and cryptocurrency, and how does the system work, and all this we'll be talking about. So basically we'll talk about Bitcoin as an application, and Bitcoin, taking Bitcoin as an example, we'll try to learn the concept of blockchain. So in 1991, this is Stuart Haber and Scott Stornetta. These two people, they wanted to implement a system where document timestamps could not be tampered with. I hope you understand the meaning of document timestamp. Like suppose I create a digital document on some particular day and time, and then somebody wants to change something with the contents of the document, the time and the date and so on. So they'll try to tamper with the contents of the document. So this should not be allowed. It should not be tampered with. So they came up with the concept of a cryptographically secured chain of blocks. And in the next year, they collaborated with some corporation, and they came up with this entire concept of blockchain. So they put forth this concept in 2008. So basically, Satoshi Nakamoto was a person who came up, who actually conceptualized the theory of distributed blockchain, and he laid the blockchain background. So this is a flowchart basically, which just tries to make things clear. Like, is it that every application you can develop with the help of blockchain technology, or you need to be selective? So what are the areas in which you can apply blockchain, or which are the applications for which blockchain can work efficiently? So if you do you need a do you need a database is the first question to be asked. So if you just, I'll not go through the entire flowchart here because I'll just focus on the main concept. So if you just travel through this flowchart, probably it will, you follow those arrows and it will bring back to the result to you that here you don't use a blockchain, or in this case, like if you're following this particular path, then you need to use a public blockchain, and in some cases you need to make use of a hybrid blockchain or a private blockchain. So we'll be talking about the different types of blockchain. So we need blockchains because we do not trust each other with transactions. So first, since it was initiated for the cryptocurrency called Bitcoin, so it is because if I want to send some money to you, okay, some amount to you. So if between us, like if I know you, it's very easy for me. I can trust the transaction. I can say that okay, I'm sending some money to a known person. So there's some trust at least between us. But if it is towards stranger, if I want to do some financial transaction with a person sitting at some other corner of the world and I've not seen him, there is only a digital presence of that person. So do I trust them? So blockchain are actually needed because we do not trust each other with the transactions, right? So in that case, blockchain is not completely foolproof. There are some problems with blockchain as well, but as of now, it is, like, we can say that it is 99% secure. Okay, so with the right set of skills, maybe, or we can come up with the concept and we can make a very secure blockchain, or we can develop a secure application using blockchains. So coming down to the concept now, what is blockchain? Now, in the simplest terms, we can define blockchain as a data structure. And it's a data structure that can hold some transactional records, and it ensures security, transparency, and decentralization. You can also think of it as a chain or records which are stored in the form of blocks. So these are the blocks. Like and in these blocks you're going to store the records. And there is no single authority, or I can say that I own this blockchain. So there's no single authority to the blockchain. It is owned by everybody. So no single owner. And we'll call this as a distributed ledger that is completely open to any and everyone on the network. And once the information is stored on a blockchain, it is extremely difficult to change or alter it. We'll see the reasons later on. Each transaction on the blockchain is secured with a digital signature that proves its authenticity. So how authentic a particular transaction is will be how secure it is. is. Like you secure the transaction with the digital signature. And due to the use of encryption and digital signatures, the data that is stored on the blockchain is tamper-proof and it cannot be changed. So blockchain technology allows all the network participants to reach an agreement, which is called as consensus. So what is the meaning of agreement? Agreement is consensus, or consensus can be called as agreement. Like if few people, like suppose in a network of 10 people, so at least 5 or more than 5 need to agree to each other or agree to the transaction. So if there is certain transaction that has been performed, so out of 10, 5 to minimum 5, maximum 10 should agree to that particular transaction that is going to take place. Then everybody will agree. So that is coming to a consensus. So all the data stored on the blockchain is recorded digitally and it has a common history, which is available for all the participants on the network. So this way, the chances of any fraud activity or duplication of transactions is totally eliminated, and we do not need any third party in this case, right? So in order to understand the blockchain concept better, let's consider an example where you are going to, like you are looking for an option to send some money to your friend who lives in a different location. So a general option that you can normally use can be a bank, or via some payment transfer applications like PayPal or GPay or Paytm. You use these mediums, right? So these are called as third party. So using Paytm, I will send money to my friend, or using GPay, any of these payment transfer applications. Now this option is involving the third parties in order to process the transactions and since these third parties are involved, we have to give some extra amount of money as transfer fee to these third parties. Okay, try to understand this concept. It's very simple. Moreover, like in these cases, you cannot ensure the security of your money, as it is highly possible that a hacker might disrupt the network and steal your money. So it is not tamper proof. There could be some hacker coming into and some fraud activity might happen. And in both these cases, it is the customer who is going to suffer. And this is where blockchain comes in. So instead of using a bank for transferring money, if we use a blockchain in such cases, the process will become much easier and secure. Okay, and there is no extra fee that is involved, as the funds are directly processed by you, and it will eliminate the need for the third party. Moreover, even the blockchain database is decentralized, and it is not limited to any single location, meaning the meaning of this is all the information and records that are kept on the blockchain are public and decentralized. Now, since the information is not stored in a single place, there's no chance of corruption of the information by any hacker. All right. So we can say that a blockchain, in the simplest terms, like very simple definition of blockchain, could be a time-stamped Now, the blockchain network has no central authority. So that is the very definition of a decentralized or a distributed system. Since it is shared and an immutable ledger, the information in the distributed immutable cryptographic primitives will have certain characteristics like autonomy, anonymity, transparency in the accounts of transaction. So we'll just define this as it is a continuously growing list of records called blocks, and they are linked to each other using some secured concept called as cryptography. What are the types of blockchain now? public versus private blockchain network. Now we have understood what blockchain is in a nutshell. So what are the variants of blockchains? So these are the variants: public, private, consortium blockchains, which is not mentioned here, but there is one more which is called as consortium blockchain. Now what is public blockchain? In public blockchains, distributed ledgers are visible to every user on the internet. It allows every user to verify and modify the block of transactions in the blockchain. And the best example of public blockchain is Bitcoin, Ethereum, Dash, and Factom. All these are cryptocurrencies. Then we have private blockchain. Private blockchains are generally incorporated within a single organization at an intra level. So within an organization, if you want to implement blockchain, then it will be a private blockchain. So only specific individuals of the organizations are permitted to manipulate the transaction blocks. Otherwise, anyone from the internet can view the contents of the block, but anyone can view the contents. But if you want to change them or if you want to edit certain transactions, then only the authorized or some specific individuals or some specific permissions are mandatory. And example of private blockchain is multi-chain and Blockstack. All these are cryptocurrencies. And finally, we talk about consortium blockchain. With consortium blockchain, things are very different. Only a group of organizations or individuals can verify and add transaction blocks. And the ledger here may be open or it could be restricted to certain groups only. And for its high security enablement, this variant of blockchain is used by organizations across various verticals. So we have Ripple, Hyperledger, if you have heard about Hyperledger 1.0, and R3. So these are the types of blockchain. Individual block in the blockchain. This is another block in the blockchain. So what is stored in the blockchain is data, previous hash, and hash. So I told you that every block has a hash value. So that is this hash. So this hash is the hash key of this particular block. And then we have previous hash. Previous hash is nothing but it is going to be the hash of the next key. Okay. So see this 034DFA this is the previous hash of this particular block. And then every hash, like this is the same block rather. I'm just showing you the same contents here. I'll show you how it is in the next slide. And every block is identified. So this fingerprint means that it is a unique identification. Every block is uniquely identified. And what does it contain? Data, previous hash, and hash. So these are the three values that it contains. So this is the chain now. So let's see how the chaining effect is formed. Now, the first block in the blockchain is usually called as the genesis block. And every block has data, previous hash, and hash value. So every block has these three values here. Now, I was talking about, so this hash is the hash of this block. This hash is the hash of this block, and so on. Now, what is this previous hash? Previous hash is nothing but the hash of the previous block. So same way, what is the previous hash of this particular block number 3? Will be the hash key of the previous block. So hash key of the second block. So see how the chaining effect is formed. This hash is stored here. This hash is stored here. So this is how the chaining effect is formed. And that is why we say that this chain is very difficult to break. So these are 5 components of the blockchain. Consensus protocol, hash cryptography, immutable ledger, distributed P2P network, and mining. If you are able to understand these 5 components and the concepts that is lying in these 5 components, I think you'll be at least familiar with what is blockchain and how to go about doing blockchain. So the first, let's start with the first part, which is the hash algorithm. That is understanding SHA-256 hash. And what is SHA? SHA stands for Secured Hash Algorithm. 256 is the number of bits that it takes. That is why we have that number as 256 here. Now let's look at a person. So here we have a person, any person, and every person is on this earth. We have a different fingerprint, and we can be identified with our fingerprint. So fingerprint is an identifier of a person. And we can say that different people have different fingerprints. Every person has a different fingerprint. So there will be very rare cases that two people have the same fingerprint. Okay. So we can say that fingerprint is an identifier of a person. And this is a very powerful concept which is used by the forensic science department, where they can identify the criminals with the help of fingerprints, because that becomes a very important evidence for them. So this fingerprint is very important. It becomes an identifier of a person. So the same concept, like how do we identify a person with the help of his fingerprints? The same concept can be extended to identifying digital documents. How do you identify digital documents? Same principle, like we'll apply it to digital documents. Okay. So if, like, suppose if we could come up with a sort of fingerprint that could identify these documents, like some fingerprint in the sense, some identification mechanism which could identify these digital documents for us, then like our documents can be very safe. So that identification mechanism is called as secure hash algorithm, SHA 256 hashing algorithm. So the algorithm behind SHA 256 was developed by United States National Security Agency. And it is such a wonderful and such a secure algorithm. We'll see the beauty of this algorithm. And it works very well. It's very secure. And a lot of places in the world where applications used to store these passwords. Like this algorithm was used by them to store these passwords. And in fact, even in blockchain, it is used like one of the core principles behind building the blocks of the blockchain. And the code for algorithm is, it's if you look at the blockchain algorithm, it's open, like you can download. It's completely open. You can download it, you can learn, and you can even understand how it works. So this is how it really identifies a digital document. So let's go in brief. So we know the full form of SHA, and 256 is basically the number of bits that it takes up in the memory. So the hash is usually always, it is 64 characters long, and it consists of digits like numbers from 0 to 9 and letters from A, B, C, D, and F. So till F, hexa, no? It's hex number. So we have this. So there's a total of 16 characters, like from 0 to 9, and these 6 characters. So 0 to 9 is 10, and these are 6. So 16 characters. And if you like, each character is in, like, each character is going to take up 4 bits, right? So we have these 16 characters, and for each character will be encrypted using 4 bits. So that comes to 4 into 64. So that is 256. 4 square is 16. So 4 into 64, 256. So this forms 256, like you have these characters. So these are 64 characters, which take up 256 bits to store in the memory. And that is why it is called as hash SHA 256 algorithm. Now, an important thing to note here is that this algorithm works not just for Word documents or text documents. Like suppose I give a PDF file. So PDF file could be, or it could be a text document, or it could be a doc file, anything, any document. You give any document, it will give you this 64 character long hash key. This is nothing but your hash key. And the hash key is 64 characters long. So this key is basically going to identify your digital documents, right? And like you can see this, since this fingerprint is identifying a person, we have this key identifying a digital document, right? So we can say that this 64 characters not only identifies a word or a text document, it works for any digital document or any digital, just anything digital. So you could just put a video into the algorithm. You can put a text you want. It could be an audio file. It could be an entire executable file. You can put the entire operating system. The whole operating system can be placed in this algorithm. But whatever be the size of the input and whatever be the type of input that you give to this particular algorithm, the output is going to be 64 characters long hash key value. Okay. So it does not depend on what is your input, how long your input is, or how, like in terms of size, I'm talking about in terms of bytes, probably how huge the input is. It is finally giving you only 64 characters long hash key. Right. So, and this is like for any input. So this is the beauty of this algorithm. So let's talk about some requirements of the hash. I'll call it as, I'll not call it as requirements of hash, but I'll say that these are the characteristics of the hash. So the first characteristics of this algorithm, or the hashing algorithm, is it is one way. One way in the sense, if I have given some document, some doc file to the algorithm, it has generated this hash key value. Okay. And then from the hash key value, logically, I should bring back the document again. I can get the document back again, but this doesn't happen here because it is one way. From the document, you can get the hash key, but from the hash key, you cannot traverse back or reverse engineer and get the document back. Okay. So basically what that means is you cannot go backwards. You cannot go from the hash to the documents. So you cannot restore the document back based on the hash key value. Or sometimes it might happen, no? Like I have, like this document is very sensitive document, and I do not want to, make it transparent. So it's very important for me. This document is important. So I have stored this in a block, and I've got the hash key of that block. So this is the hash key of that block. So when I get the hash key of the block, and if this hash key accidentally is happens to be taken by some other person, then it might happen that you using the hash, the document can be found. But the hashing algorithm takes care that from the hash key, you will not be able to get the document back, right? It has to be like the fingerprint, like for a human. If you have the fingerprints, you cannot restore what the person looks like. You cannot really understand, like, the color of, like suppose, a person who's, the color of his eyes, or maybe his complexion and so on. So all the details or the features, how the person looks like. So from the fingerprint, you cannot get all these characteristics of the person. So that's the same thing. It's one way. Okay. And at the same time, like if you have a person, any person, you can find the fingerprints, but from the fingerprints, you cannot find the person. So it's one way. Deterministic. So when we say that it has to be deterministic, meaning that if I take the same document, exactly the same document later on, and I run the same hashing algorithm on it, then what will be the result? I should get the same key, isn't it? The documents are same. So it has to be deterministic in the sense, even if I duplicate the document and give it to the algorithm, it's going to give me the same hash. So it will not mean that today if I give this document, it will give me a different hash, and tomorrow if I enter the document, the same document, it will give me a different hash. No, it will give you the same hash key. The third is fast computation. Now this is so important that whatever, like I told you, whatever is the size of the input, the computation or the algorithm runs so efficiently and so fast, the speed of computation is so fast that it immediately within seconds, it gives you the hash key. So that is, and it has to be that way, right? It has to be very fast. If it takes 5 minutes to give me the hash key value, it's not going to be useful for blockchain. And next is the avalanche effect. A very important requirement of the hash is avalanche effect. Now, now look at this. Like if you look at the previous slide, okay. So we had these duplicate documents. So even if you duplicate the documents, the hash key value is going to be same. But now suppose I want to do some tampering with the documents. So this document is same, and in this document, I'm just adding some extra content, be it a single dot, be it a single character, a single alphabet, a single symbol, anything. You just add a single extra symbol, it changes the hash completely. Now, if you look at these two documents, both are same. With this addition of +1, I got an entirely different hash key value. And this document has a totally different hash key value. This is the avalanche effect. The average effect means that if I take exactly the same document and I change it, just make a tiny little change in that, the entire hash key value changes. Okay, so this is a very important characteristics of the hash algorithm. And last is it must withstand collision. It must withstand collision in the sense, what is like I'm talking about static collisions. Like if suppose here, like I have the same documents here. So obviously two documents which are like same copy of each other, like duplicate documents. So the system should understand that it is giving rise to the same hash key value, means this document is a fraud document, or we can call it as a duplicate or a tampered document. It has been produced exactly similar to the original document, but it is hashing into the same hash key value. So this is collision. And just to explain this better, if you have learned theoretical computer science, we had one algorithm there which uses the pumping lemma. If you have heard about the pumping lemma, in the pumping lemma, we use the concept of pigeonhole principle. So this is the same pigeonhole principle here. So it means that if you have two duplicate documents, it will go to the same hash value. So if you have the number of pigeons are more here. So more means this pigeon is a duplicate pigeon and it is hashing into, or it goes into the same hole, or it is hashing into the same hash key value. So the pigeons, you can have the analogy in this respect, that the pigeons are the documents and these holes here are the hash key values. So it follows the principles of this. So in case the collisions are forged. The next is, so now we talked about what is hash cryptography. Now we move on to what is immutable ledger. So this immutable ledger is, see, all these blocks, we have seen that the previous hash value is the hash of the previous block and so on. So all these blocks are cryptographically linked together, and this is where the chaining effect is formed. So let's take an example here. Now suppose you are purchasing a house and you make a sale deed, and using the sale deed will have your name, right? This document is very important because this document is going to guarantee that I am the owner of the house. And usually in the original systems, what it was there were some traditional ledgers, and they used to maintain these ledgers, and in these ledgers they used to make an entry like, this is the owner of the house, who is the owner of the house, what date, what time the deed was made, and so on. So all these information is being used to be stored in these digital ledgers. Now if this digital ledger is tampered, like it's very easy, it is just like a book, like a register, and you make manual entries in this register. So you can tear those pages, you can scratch and write some other's name and so on. So anything could happen to these digital ledgers, it could be tampered with. And then how do you prove that this house belongs to you? So why not store this entire concept of buying and selling properties into blockchain, such that if I have purchased the house, that particular transaction will go into the first block, and later on different blocks will be developed. So what happens is, when I am the owner of the house, if this is a transaction that goes into the first block of the blockchain, then no one else can tamper that, because it's that, like, even if there is a very efficient hacker, even that hacker cannot go and change the data within the blockchain. It's very difficult. So the ownership is preserved, and it's not going to be tampered with. Nobody can go and change or make some corrections in the ledger and say that, okay, me instead of XYZ, ABC is going to be the owner of the house and so on. So such things are not going to happen. And this is a best example where blockchains can be used. Now suppose that let's assume a scenario where even a blockchain can be hacked. Suppose it's not possible, but let's imagine that this also is, like, at some particular location there is a blockchain which is hacked, and so if the blockchain hash key changes, then the remaining chaining effect is broken. I hope you get this. Because if the hash key of this particular block changes, the previous hash of this block will change and so on. So it will happen to the subsequent blocks. See, so if one block has been tampered with, the remaining blocks all will be tampered. So the chain will be broken, and we can immediately understand where the tampering has happened. So it's very easy. So this is how blockchain, the beauty of blockchain is. Now the third concept is distributed P2P network. Now, so this is a network. It's distributed. Suppose in this network we have got some 6 nodes. So in a distributed peer-to-peer system, we have got lots of computers, and they're all connected, interconnected. Like interconnected is, I'm talking about, see, in the majority of the machines it is going to be connected. So they're all interconnected. Ideally, the more they are connected, the better. So, but of course we can't, possibly try and connect to everybody at the same time. But through the network, everybody is interconnected. So suppose I say that this node is not connected to this, but through this node it is connected. This node is connected to this node, and this node is connected to this. So I can say that these two are connected. So through the network, everybody is connected. So this is how the blockchain is going to be stored. So blockchain is actually copied across all the nodes or all the computers on the network. So let's think about our example for properties. Instead of just keeping it on one system, it is actually copied across thousands and thousands of computers. So here we just have 6 computers in this example, but it can be actually thousands of computers or even millions of computers, because it's a distributed network across the globe. And everything, so we are connecting all these through cryptographic keys. Now suppose a block has been added at every peer. So this is how it gets. So if it gets added at one node, it has to be copied to all other nodes as well. If a block is hacked at some peer. Now see, so these are the blockchains. It is same for all the peers. The blockchain is going to be same. The number of blocks in the blockchain has to be same. Otherwise, they are not going to come to an agreement. So whatever the blockchain is there at one node, that same blockchain has to be present at all the other nodes. Now, if this is tampered, okay, some block has been hacked, and it is this chain has been hacked only at this particular peer. Now what will happen? The subsequent blocks have changed now. So all these blocks are going to be delinked, because we have that concept of previous key and hash key, right? So all these blocks, the subsequent blocks are also changed. Now the other peers in the network will notify this hacked peer that it has a blockchain which is different from all others. So this neighboring node will send a message to this node. This node will send a message. This node will also send a message to the hacked peer saying that your blockchain is different than ours. Then what they will do, after they get consensus from majority of the peers, right? What do I mean by majority of the peers? In this network, we have 6 nodes. One is hacked. Okay, so 5 are remaining. So out of 5, majority of them are sending a message to the hacked peer that your chain is different. So that is 1, 2, and 3. 3 of them are sending a message. So it becomes majority. So majority of the peers will inform them, and after it is informed, it will realize that, oh, it has a blockchain which is different from others. So what will the hacked peer do? It will update its blockchain to whatever the peers have. Now coming to the concept of mining. What is mining? Why is it important? What is mining? Why is it important? And so on. Like, why are so many resources that are allocated or they are dedicated to mining blockchain, to mine the blockchains, right? So how mining works. So this is our block in a blockchain. So we have a block. So let's add the contents to the block. So it has got some couple of fields. Okay. So first of all, it will have the block number at the top. Then it has got some data. And as you can see, I have put some fake data, like where I'm sending, 100 rupees. X is sending 100 rupees to Y. X is purchasing something of worth 1,000 rupees from Amazon. And Y is sending 900 rupees to Z. So some transactions, okay? So this is how I'm representing the transaction. Now notice that the block does not contain only one transaction. It may contain multiple transactions. Because you know that the size of the block is also important. So Bitcoin size of the block is 1 MB. Every block is of size 1 MB. So in that 1 MB of block size, you can store as many transactions as possible. So there are multiple transactions that are stored in the block. Then also in the block, we will have a field which is called as the previous hash, because this is the field where linking is going to, the chaining effect is going to happen. Okay. Previous hash, or we'll call it as the hash of the previous block. And this is a very important feature of blockchains because that's how the cryptographic link is facilitated between them. And then in this, finally, we have the hash of the current block, the hash of the current block. And how do we get the hash of the current block? Where we take the, for getting this particular value, the hash key value, we take the block number, we take the data, and we take the previous hash. All these three will be fed into the SHA-256 algorithm and it will give us this hash. Okay, so this data is important. So can you just pause and think about it? Like if I am generating the hash key for a block using the block number, the block transactions, and the previous hash value. So a small change to any of these three fields will change the hash. Avalanche effect, it will change the hash. So instead of X giving 100 rupees to Y, suppose I remove 10 here. Then what will happen? The entire hash value will change. So the transactions cannot be tampered now, because transactions also form or also are the major role of defining the hash key. Now, is it so easy to generate the hash? Like you have the block ID, you have some data, you have previous hash and the hash value. So an important question is it so simple to just take the block number, the data and the previous hash, you put this data into the hashing algorithm and get a hash value, and the hash value that we get is within seconds. So if it's so simple, then what's the whole what is the concept of mining here? How is mining related to this? So here we talk about, like hundreds of thousands of mining rigs that are around the world, are like nodes around the world, and these mining rigs are basically used for doing the mining job. And there are so many miners across the world. Now if you talk about Bitcoin, for mining the transactions of Bitcoin, there are so many miners. They are across the world. There are many miners and they compete with each other to mine the transactions of Bitcoin. So for mining, we need to talk about nonce. What is nonce? Nonce is an abbreviation for number used only once. Number only used once. So basically it's a number which is added to a encrypted block in a blockchain, and when you rehash it, it will meet the difficulty level restrictions. Now the nonce is basically a number in the blockchain for which the miners are actually solving the puzzle. Now this is a field where mining is going to happen, nonce. And this field is basically related to mining. So if you change this nonce, they're trying to solve the cryptographic puzzle. So I'll speak about this in detail. So you have, now initially I told that we have the block number, the data, the previous hash, and the hash value for every block. But now we add one more field which is called as a nonce. So this nonce get added here now. So slowly, I'm trying to change the contents of the block now. What are the additional fields and why they are required? Okay. So nonce is basically used for mining, because mining is basically what that if I initiate a transaction and I want to add it to the block, so it does not directly get added to the block. Okay. So if this transaction, it is verified, the transaction has to be verified first, whether it is a genuine transaction or it is a fraud transaction. And this verification is done by miners. And these miners also cannot directly verify the transaction. They have to solve some puzzle, some mathematical puzzle. And once they solve the mathematical puzzle, then they say that, yes, this transaction is validated. Now you can add this transaction to the block. And then the transaction gets added to the block. So this is how secure it is. Okay. So what controls or dictates the hash? So what is it that will now dictate the hash of the block in this new updated structure is the nonce value now. We have seen this, like, see this, the green box here, the green box where you have the block ID, nonce, data, and the previous hash. Now all these four key values here, block, nonce, data, and previous hashes, these four key values are now going to be used to give this hash value. All these four components, we put them into the hashing algorithm and then we'll get the hash value. Now this nonce gives the extra flexibility. The hash value can be manipulated by changing the nonce. Now if I want to change this hash value, I can manipulate the nonce value. The block number, the data, and the previous hash cannot be changed because blockchain is an immutable ledger. Immutable means once things are gone into the ledger, into the block, it is, you cannot change it. That is the meaning of immutable. Now we can manipulate the hash value by changing the nonce. So we can't change the block number because the block number in the block is the block where we can change the previous hash, because it's linked directly to what we have in the previous block, and we can't change the data because that would mean tampering with the data. And if you tamper with the data, it will defeat the whole purpose of having a blockchain because it is immutable in nature and we have to prevent tampering. So now because we have the nonce, we have to we are free to change the value of the nonce, and the nonce is basically a number we are free to change. So we can change the nonce, we can manipulate the value of the nonce, and we can arrive at different hash values. So changing the nonce will change the hash value. So if this nonce value is 19, it will give me this particular hash value. If I change it from 19 to 20, it will give a different hash value. So every time you change the nonce, it will give you a different hash value. Now I have made the nonce value is 23. It changes the hash value dramatically. So the hash value that you get is completely different than the previous one. And that is very important, and that's the avalanche effect. And actually, this is how it happens. Avalanche effect is even if you're changing a small thing in the block, the entire hash key value changes. Now this nonce is a very huge number. Now I'm just putting this as 1, 9, 12, 23, but it is actually a very huge number. It can go up to 4 billion. So it's quite a large number, and there's a lot of variety that you can play around with this nonce. And so if you have, can you imagine, like if you have hash, the nonce value ranging from 0 to 4 billion. So how many different hash values can you get? So it's a huge thing that we're doing, right? So this is what we're talking about, hash. So hash is basically the number. This is one number. So hash value, as we've already seen, it contains 64 characters. So let's talk about this hash now. So decimal equivalent is so many numbers, and you have this numbers. Now this is also a hash number, but it is preceded with so many zeros. You can increment the hash. You can you can do all the mathematical operations on this hash. So hash is basically a hexadecimal number containing digits from 0 to 9 and alphabets from A to F. And we can actually convert this hexadecimal number into a normal decimal number also. So this is the decimal equivalent of this particular hash number. Okay, decimal representation. Because in the decimal number system, we just have 9 digits. And in hexadecimal number, we have so many digits, as already said. So in decimal number, we have 10. So this is another SHA-256 hash, as you can see. And this is starting with so many leading zeros. So if I want to introduce complexity or make my hash key very difficult, so you just you just append, or you just prefix, not append, it is you just prefix it with zeros. So the more the number of zeros, the more it is difficult to get the hash value. Okay, so you can convert this to a decimal also. So if you convert this to a decimal, you get this. So this is another hash with so many leading zeros, and converting it to decimal. So now talking about pool of hashes. So just try to understand the concepts, like why we are talking about hashes here. So this is a pool, and it will contain all the hashes here. Now, can you imagine like how many, what will be the count of hashes that will be there in the pool? Like initial, like you have to, since it is 64 characters long, the first hash value will be what? Like the minimum one, the smallest one. The smallest hash value will contain 0, 0, 0, 0, 0, 64 zeros. So 640 is the smallest hash value. Smallest in the sense, it's not smallest in terms of numbers or something, but we'll see that what will be the range of this hash value. So the first hash value will begin with 64 zeros. And what will be the highest one? It will be 64 Fs. F is the largest alphabet which is there in the hexadecimal number. So F, 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 F 64 times. And in between these 64 zeros and 64 Fs, can you imagine how many different hash values will be there in that? Okay, what is saying, like what are the possible variations of this hash value starting from 64 zeros to 64 Fs? They're going to, like, you can't even imagine how many hash values will be there. So initially it will be 64 zeros, then it will be 63 zeros and then some character, then it will be 60, suppose 63 zeros and A, then it will be 63 zeros and B, 63 zeros and C, and so many different combinations. So that is why we are calling this as a hash pool. Now in this hash pool, they are not arranged in a sequential manner. The hash values, or the 64 hash values, they are not arranged in a sequential manner. They're random. They're anywhere. I may have, all zeros with 64 zeros at the top and all F's at the bottom. It could be anywhere. They're not in a sequence. So when I'm searching for a hash value in the hash pool, suppose this value lies somewhere here, this value lies somewhere here, and this hash value somewhere here. It could be anywhere, right? Now suppose, now we are just concentrating on these. Like I have these 3 different hash values. So this is probably preceded with maybe 10 or 12 zeros, and here some 20, 30 zeros. Okay, so this is one hash value without any it is not prefixed with zeros. This is with some zeros, and these has almost 50% of them are zeros. So how mining works, in a sense, the blockchain in the blockchain system, or the blockchain or the hashing algorithm, is that we have to set a target. There is a target which is given to the miners to accomplish. Okay, to accomplish a certain hash. So what is this target? Now suppose this is the target. Now in this pool of hashes, this is the target line. Okay. Now the blockchain algorithm will set a target for the miners to accomplish a certain hash. Any hash above the target is not going to count. So if the miner has to find a particular hash, the target is given that it has to search for the hash value which is only in this particular range. If it goes above the target, it is not a correct hash. So the target is set just to make the puzzle difficult. So this is the puzzle. This is the puzzle that the miners have to solve. They have to search for a hash value which is within this target. Okay, and setting the target is obviously going to make their job more difficult or more complex. If a miner finds a target within this particular target, then it is correct. Otherwise, it's going to be a false start. Now, suppose we have this like a good way of thinking about the target is actually in terms of leading zeros. So when you have more number of leading zeros, this hash value could become a very good target, because it's very difficult to find a hash value with so many leading zeros. So the smaller the number and the more leading zeros will be there. So you have a very small hash value, but leading zeros are more. So if you think of the target in terms of hashing, then a good way to start is start with 4 leading zeros, and you set a target for that. Now here, except nonce, nothing in the block can change, right? So we have seen this. So apart from nonce, all other data in the block is not going to change. So now suppose for this particular nonce value 23, it found a hash key, and that hash key is somewhere here. Now here I have not listed all the 64 characters of the hash, okay, but you assume that it is 64 characters. So just for pictorial representation, I could not add all the 64 characters, but the previous hash as well as the hash value are 64 characters long. Now for a nonce value of 23, I found a hash which is here. Okay, so this hash value is found at this particular location. So is it a valid hash? No, because it is above the target, right? So this way the miners have to go on changing the nonce and find a hash. And if it finds the hash which is above the target, it is not going to count. So see, now it has made the nonce values 22 and it has hashed here. So that is also not correct. So it goes on changing. So what happens is, see what value for nonce 76943, because we have seen that nonce value ranges from 0 to 4 billion. So you can add any number. So it is just trial and error. What the miners are doing is they're trying to uh, just by luck, they assume something, they randomly put in some nonce value and they find the hash. So they try to hash here. This is also not working for a nonce value of 177. Now you get, now for a nonce value of, suppose for a nonce value of 5012, the miner gets a hash which is within this target. So the miners win because they find a hash which is within the target, and the nonce is going to be called as a golden nonce. Now the miners can then add the block to the blockchain. Now this block, which is validated by the miners, will be added to the blockchain. And for solving this, whatever puzzle the miners have solved, they will get a reward. So the nonce are located randomly in the hash pool, and they are unpredictable. So you can't do a sequential search here or a linear search. Okay. So the whole concept of finding the correct hash is called the cryptographic puzzle. Now this is with respect to Bitcoin. Now Bitcoin has this type of cryptographic puzzle, and because it's a public blockchain, it is across the globe, and people are trying to. There are various miners on this Bitcoin. Miners are nothing but they are additional nodes in the blockchain, and they have a high computing power so that they can solve this puzzle. And these puzzles are very complex, so they need high configured machines for doing this, solving this puzzle. Yeah, and now this concept of Byzantine fault tolerance. So this is a general concept which is actually used in many applications or in many programs. It's a very important characteristics, not only used in blockchains but also for any type of decentralized system. Okay, Byzantine fault tolerance. So I'll just explain this with a short story. So the story goes that a long time ago there was a castle. So this is a castle, and the Byzantine Empire wanted to attack and take over. The four generals, so we have these four generals, they wanted to attack the castle, but they can only win if majority of them come to an agreement or they come to a consensus. So out of four, if three decide to attack the castle, they will attack. Out of four, if three decide to retreat, they have to go back. If they disagree, then obviously they are going to be defeated by the army. And coming to a consensus is very important for them. If they don't come to a consensus, they are going to get destroyed. So one general is the commander. So we'll call this general with the crown is the commander, and one is a traitor. Okay. Out of these four, one is a commander and one is a traitor. Traitor is one who's going to cheat. Now the traitor is unknown, and what will the traitor do? He will try to create hurdles in the way so that the consensus will not be achieved. Okay. If three of them decide to attack, or if the commander issues a message of attack, the traitor will say it is not attack, it is retreat. He'll send the opposite message, or he'll try to create hurdles. Now, pool of hashes. Now, what is this pool of hashes? Each general can communicate with the other by sending and receiving messages to each other. So these arrows are nothing but sending and receiving messages from each other. So this general is connected to all the three other by sending and receiving the messages. Now suppose this one is a traitor. This highlighted person here is a traitor. The commander also can be a traitor. Anyone can be a traitor. So this is actually a very complex mathematical problem. Now the commander issues order of attack. Okay, so the commander, this green arrow, he sends a message to this general, attack. He sends it to all three of them, attack, attack, attack. Okay. Now what will the traitor do? He'll do the opposite now. The traitor sends a message that the commander told him to retreat. So this green arrow here, this orange arrow here means this traitor sending a message to this general that the commander has sent me a message to retreat. So he's doing some fraud activity here. And here also for this general, he cannot send it to the commander. Okay, so he sends it to the other two generals. Now the other two generals say what the commander orders them. Why? Now the question here is, even if this traitor is sending a message of retreat, the question is, will they come to an agreement or will they come to a consensus? Okay. Now if you look at this particular general here, how many attack messages this general has got? This person is genuine, so he also has sent a message of attack. So commander has sent a message of attack. This general also has sent a message of attack. Only the traitor has sent a message of retreat. So maximum, which are the messages that he has received? Attack. So this person will attack. Okay. Now coming to this person. This person also has received an attack message from this general, attack message from the commander, and retreat message from the traitor. So majority which messages? Two attack and one retreat. So this person will also attack. Now what is happening? Are they coming to a consensus? Yes, they are coming to a consensus. Why? Because The commander is genuine. He has issued a message of attack. So the commander is attacking. This first general is attacking. This second general is attacking. So out of four, three of them are attack and one is retreat. So they come to a consensus. Majority of them have the same message and they will attack the castle. Now let's imagine another scenario where the commander itself is a traitor. Now what will happen? Will the algorithm still work? The Byzantine fault algorithm. Will the algorithm still work? Now the answer to this is yes, because all the other three generals will do what the traitor says. If there are two traitors, then will the algorithm still work? You can think on this question. Now, when the commander itself is a traitor, the commander will either send an attack message to this, retreat message to this, attack message to this. So you see whichever is the consensus. So whatever message the traitor says, now the traitor cannot send different messages to different generals, or can the traitor send different messages to different generals. So in that case, the algorithm will still work because all three of them are going to do what the traitor says. Because see, if this traitor sends an attack message to this, and a retreat message to this. So of this, both of them are in consensus, like they are in agreement because they will get an attack message here. They will send. So majority messages will be of attack. You try it out. It will work. Now, next variant of this could be if there are two traitors, then will the algorithm still work? Now, if this person is a traitor and this person is also a traitor, now the algorithm will not work because they will not get consensus, maximum agreement. So there is a rule that has to be enforced saying that 1/3 of the army cannot be traitors. 1/3 is 33% of the army cannot be traitors. For example, if there are 10 generals, then maximum only 3 of them can be traitors. If there are more than 3% as traitors in the system is not going to come to a consensus. So this is you can say that this is the level of tolerance of the system. Now, this was just an example for you to understand, but actually this is related to our blockchain technology. Like these generals are nodes. Okay, these generals are nodes and they are going to send and receive messages to each other because they are connected in a distributed network. So if majority of the nodes come to a consensus, then only the transaction is validated and added to the block. Otherwise, it is not added. Okay, so and this particular rule, like 33% of the army. So out of 10 generals, maximum only 3 can be traitors. If there are more than 3 people as traitors, the system is going to collapse. It is not going to be fault tolerant. Okay, so this was just an example. Like if the traitor sends attack to this general and retreat to this particular, still the system will come to a consensus. And there are various applications of this Byzantine fault tolerance. This concept is basically used in many different places. In airplanes, which contains many small systems which are talking to each other. And even if like one or two of them fail, you just can't, allow the whole airplane to crash. So the system has to be fault tolerant. Otherwise, it's going to be very critical. So this algorithm is basically used there. And in nuclear power plants, these are very real-time applications which are running 24/7, and they have to be fault tolerant. So all the characteristics of Byzantine fault tolerance is used in this. Okay, nuclear power plants or even for launching the rockets. You see many of these applications use Byzantine's fault tolerant. So we have completed all these 5 components: consensus protocol, immutable ledger, distributed P2P network, hash cryptography, and mining. Right? So let's, sorry, the last one, the consensus protocol. Now for the consensus protocol, you need to understand the concept of these challenges first. Now, the Byzantine fault tolerant protocol, like what we learned in the previous slide, is basically used in the distributed network. Now, the question is, how does it agree on how to keep growing? How does it agree on how to keep growing, in the sense, how are the chains which are located at every node? How do they agree? Like if there is a block which been added to this particular node, then how is it going to tell the other nodes, and how the chains in the other nodes are going to be replaced? How do you keep adding blocks, in which direction, and how to know when to add a block? And so the challenge is that a consensus protocol in the Byzantine fault tolerant example, that the challenge for the general was to understand which command to listen, whether to attack or to retreat. And then they had to come up with a consensus. Now, the consensus protocol for the blockchain has to solve two main challenges. Number one, protect the network from attackers. And we've already talked about the situation where an attacker tries to attack somewhere in middle of the chain. So if an attacker tries to change the block in the middle, then that's going to be almost impossible for them, because they would have to change all the remaining blocks, the subsequent blocks. So that's not the problem that we are looking out here. The problem is different. So what is the problem here? Let's try to understand this. So attacker tries to attach a block at the end of the chain. So somewhere at this particular node, the block has been added. Okay. Now the problem we talk about here is, we are not talking about any fraud activity or any malicious block. It is a genuine block. So it's nothing about fraud. Okay, it's a genuine block. So this block we are trying to add. So this, now when this genuine block gets added here, how are we going to add this particular block to the other chains? Okay. And so this block either could be malicious, either could be not malicious. If it is not malicious, it will be easily solved. It will be added to the chains here, because this block, if it is a genuine block, it will be validated by the miners by solving the cryptographic puzzle, and it will be added to all the other chain. Now, if it is a malicious block, then what will happen? How will it be validated by the miners? And then if it is validated by the miners, first of all, if it is malicious, it will not be validated. So there itself, this block will be discarded. It will be said that this is a malicious block and it cannot be validated by the miners. It will never be validated. And if it is never validated, it will never be added to the blockchain. So this is the challenge one of attackers. And the second challenge is related to the competing chains. So in a large blockchain, because it is distributed across the world, there can be a lag between nodes, especially those that are far away from each other. And it could so happen that the two nodes that are far away from each other could successfully mine a block at the same time. You can imagine a situation, right? I'm talking about two blocks. See, one block, it is a genuine block which is added at this particular node. Now this node is suppose somewhere in the US, and this node is in India, and this is one node which is getting added to the blockchain. Now both are mined, both are genuine blocks, both are getting added. Now see, there's a problem. If you see, all the chains will be different, right? This chain at this node is different, this chain is different, and probably because this node is closer to this node, this chain will be accepted by this node. And this node is closer, or this node is closer, it will accept this chain. So the nodes are having different chains now, right? So how do you solve this problem? So this is one of the challenge here. And the blocks are genuine. We are not talking about malicious blocks here. The chains are genuine. So the same block is being added at different peers, right? So there's a solution to this. So now I don't have that much of time to discuss on the solution, but the problem of competing chain is solved by, there's a rule which is made. And So at present, they leave the blocks as it is. If this block is added here, it is left as it is. This is also left as it is. And then maybe eventually after some time, some more blocks will be getting added. Suppose in this chain, there are 2 more blocks getting added, and this chain does not add any of the block. So the rule says that whichever is the longest chain will win. So if this chain, after adding this particular block, has added few more blocks further, this chain will become longer than this chain, and then the longest chain will win. So longest chain will be added to all the other nodes. It will be replaced. Okay. And there are various consensus protocols which actually do this. So proof of work, proof of stake, and there are some more, but these two are the most popular ones. And these are the consensus protocols which are basically used. So proof of work is used in Bitcoin, right? So that is how this happens. I'll just quickly talk about cracking the hash by guessing the nonce. So we see that the miners are basically changing the nonce value to get the hash which is within the target. And once it gets that, that is the golden nonce. So miners are rewarded by the network or by blockchain. So if we have a Bitcoin blockchain, so miners are going to be rewarded by Bitcoin. Bitcoin will give them some reward. So this is in terms of Bitcoin. So if this particular block is mined by this node, then they will get a reward. So so miners also get some fees that are associated with the transactions in the blocks. So because in a block, there is not a single transaction, there are multiple transactions. So miners get some fees which are associated with the transactions as well. So that is called as some monetary incentives. So how will the network know that a malicious block has been added? So when you talk about when the malicious block is added, how do you identify those, right? So before the newly created block gets added, each node conducts a series of checks, which is very rigorous. And before the block gets added or it is propagated to the network, every single node has to conduct this series of tests. So these are some series of tests. And they check that whether that particular hash, they check for the proof of the previous block matches the previous hash field of the main block. So you check for the cryptographic links are also checked. So now like this becomes an advanced topic of blockchain, but just understand that these are some series of checks that they perform. Then how to resolve the conflicts. So about the competing chains, which chain wins? 2 miners mine a block at the same time. Then here we get a conflict in the chain. So how is the conflict going to get resolved? So this is where the consensus protocol comes in picture. So this is the Byzantine fault tolerant example. So what happens is, and we assume that this is a fair block, it's not a malicious block. So once it is going to be propagated, or if it is relayed through the network, now you see this block is relayed here, relayed here, relayed here, and this is propagated to these two only. Okay. So whichever communicates faster, and the chain which, see, so it is communicating now. So all are trying to communicate. Whichever communicates faster, that chain gets replicated everywhere. Okay. But still, all the nodes do not have the same chain. So what happens? See, eventually in this chain, one more block getting added, one more block. So all of this. So this chain becomes longer than this chain. Then what happens? Finally, see, since this chain is longer, this chain is getting replicated everywhere. So it will be replaced, and the blue block that was added to the chain is thrown out. It will not be added to the block, right? So, and even the reward, like when the miners had mined this block and added to the blockchain, the reward for adding the purple block is also not valid. So it is because it is not it is called as an orphaned block. So this particular block is called as an orphaned block because it is thrown away by the blockchain. So then finally you have the same blockchain at every node. The blocks are added, the consensus is achieved, and then every node has the same blockchain. So this is the entire basic fundamental concepts of blockchain. So if you have any questions, maybe I can take on those.